In chemistry, we're constantly having to measure things in order to find out how much of it we've got. And that's because we just don't have the ability to tell how much is there without using some sort of a technique. Molecules are simply too small for that. We can't count them with our fingers. We can't count them with our toes. We've got to use instrumentation for it and clever approaches that use chemistry. Now, let's set up a question to explain what we're doing with a titration. Suppose we want to measure how much of some compound, X, is present. I'm not going to specify what X is, but if you want to have something to think about, you could picture it being H plus or OH minus. Now we know that we can react those in a 1-to-1 ratio, right? Well, same idea. If X reacts with some other compound, Y, and we know what ratios they react in, we know the stoichiometry of the reaction, we could do some sort of a reaction where we know the concentration of one. By measuring the volume needed for the other, we'll be able to find out how concentrated the other solution will be. Let's see exactly how that works graphically. So suppose we have our balanced chemical equation. 1 unit of X plus 1 unit of Y yields XY. And also I'll stipulate that all of these are going to be clear. They could have colors to them, but I don't want us focusing on their color change. Instead, what we're going to do is we're going to add an indicator solution. And in the very moment that we run out of both of these compounds, we want the indicator to change color. Realistically, the way that really happens is that if I'm titrating Y, my unknown, I'll keep on adding some X. And it'll always be reacting with all of the X. So I'll always end up having 0 X plus, some Y minus, and I'll be generating some of this. But anytime I add a drop, this disappears. Right up until the moment that I'm all out of Y. In that moment, I'll suddenly have X in the solution, and my indicator will change colors. Now that brings up a concept called endpoint and equivalence point. Equivalence point is the moment where I added exactly the same number of moles of X plus and of Y minus, or at least a stoichiometric ratio of the two. Since it's a 1-to-1 ratio, it'd be the exact same amount in this case. Now, I said that it doesn't change color until I have extra X plus around. That's the thing that we're going to see with our eye. That's called the endpoint. The endpoint is always going to be slightly bigger than the equivalence point. If you want to think of it like this, the equivalence point is the one that you're aiming for. The endpoint is the one you can actually see. And you'll want to try to make sure that they're as close together as possible with good laboratory technique and careful selection of the chemistry that you're going to do for your indicator solution. I'll leave the details of that for another time. But let's go ahead and take a look at this. Now suppose that when X and Y are gone, my solution is going to change color. And let's set it up like this. Let's make a standard solution where I took a bottle of X plus salt off the shelf and I made a really well-known concentration of this. Now I'm just showing it generically with numbers. We put in real values here, of course, but right now I'm going to keep it just very abstract and conceptual. We're going to do whatever we can to make sure that this concentration isn't going to change and is really, really well behaved. And that's a process that we call standardization. We'll pick a molecule that's very good and stable once we standardize it, so that we have a well-known solution that doesn't drift. Some things will react with oxygen in the air. Some things have problems with other molecules being around and slowly react away, or they start sticking to the glass, or they're hard to measure because they get waters of hydration. All these things are terrible when you want a standard. You want to have something that's really well behaved and really simple, and ideally really cheap. So that's one of the reasons we use hydrochloric acid so often. It fills those roles very nicely, so HCl is great for this sort of thing. But for the moment, we'll just say, for lots of experimental reasons, we've picked what we're going to use as X plus carefully, and this solution is well standardized. We know this concentration really, really well. However, we don't know the concentration of Y in this solution over here. It's our unknown. So what can we do there? Well, since we do know a balanced chemical equation, we can take some of this standard solution and put it up here in a burette. Now we'll record our starting value, and it's probably not going to be the value 0, because we're going to bleed out any bubbles that are in the line and prepare our experiment and everything. And we don't really need it to be 0. In fact, it's kind of hard to read it at 0 because remember, when you read glassware, It's really helpful when you have those little markings above and below a line. At 0, you don't. So it's really hard to guide the eye and get exactly a good reading with significant figures. Anyway, we'll have our initial volume. So what we're going to do is we're going to add some volume. We haven't had a color change yet. We'll keep adding volumes until finally we do see our color change. Now keep in mind there's that endpoint versus equivalence point issue, but let's say that we have really good lab technique in this example and we nailed it. Our endpoint and our equivalence point are effectively the exact same value, plus 1 molecule. By measuring the volume that we had at the beginning and the volume we had at the end, the distance between these two tells us the volume that we actually added. So we now know the volume that we used of our standard solution. We know the concentration and the volume, and that means we now know the number of moles of X plus. Because we know the stoichiometric ratios between X plus and Y, we now know the number of moles of Y. And since we know the volume that we had there originally, we know the original concentration. That's the basic idea behind a titration. So keep in mind, this is the end game for it. How much volume of X plus did you have to add to Y minus? Then you figure out how many moles of X plus you had. From that you can find out how many moles of Y you had based on your balanced chemical reaction. And finally you'll use that volume, if you wanted to get to moles and molarity, you'll use that volume in order to get to molarity for the unknown. That's how we perform a titration conceptually and how we handle the mathematics for it.